Okay, good afternoon, all of you. Welcome to this lecture of refrigeration and air conditioning. So, at the start, I asked one question, like how many holes does a straw has? Okay, so this question was popped in YouTube recommendations when I was searching on YouTube. So, lot of videos are there on this also, but uh, this question has different answers. So I have seen videos, so each video has some different answer to this. So others also can think and they can answer. So I have two answers here, like zero. So both are same, I think. Zero and straw does not have holes. It is a pipe. Okay. So I'll give options also. So either it can be two, it can be one, or it can be zero. Okay, so I'll try to answer. So I have seen some videos. They have this answer for like how many. So for a straw, how many holes are there? For before that, we have to understand what is a hole anyway, right? So hole, as we have studied in manufacturing processes or even workshop practices. So if I take a sheet of metal, so if I use a drilling machine, so I create a hole inside a sheet. Okay, so suppose this has very minimum thickness. Okay, so it may be 1 mm thickness is there. In that case, we are calling this as a hole. But what happens if I take thickness? Okay, if I take a thickness, so this sheet has some thickness now, and if I drill a hole at that time, uh, so this will be a hole for that sheet with the thickness. That time also we are not saying that it is having two holes. We say that it is having a one hole. So in this case, it was a one hole. Here also it is a one hole. So one video was there that he's saying that the straw has only one hole. But thing is the hole of a straw. So if I draw a straw here, okay, so this is a, suppose this is a straw, and so these are the faces. So this is a phase one, phase two, and if I take this surface, that will be phase or surface three. Okay, so if I take an example of a box, and its all faces are closed except the top surface. Okay, so this top is open to the atmosphere, but we cannot say that this box has one square hole. Okay, so we can say that one of its face is open to the atmosphere and all other faces are closed. So we cannot say that this is a hole to the box. Okay, so similar approach if you use in the case of straw, we can say that these two faces are open to the atmosphere and one face is, or one surface is closed. So I agree with Pradyumna that pipe, we can consider straw as a pipe. So in that case, the straw does not have any holes. So if I ask that straw, for a straw, how many holes are there? So you can say zero. So this is one analogy I'm using of box. But if you take this analogy of this sheet with a thickness, in that case, that hole we can count it as a one. Okay. Okay, so we'll begin our today's lecture. So welcome to this lecture of refrigerant air conditioning. We are now in the chapter third, that is the refrigerants. So refrigerants, as we have discussed in the first chapter also, these are the heat carrying mediums. So refrigerant, we can consider them as the blood of this VCRS system. So they carry heat from one location to another location. They extract heat in the evaporator, then they carry this heat to the condenser. In condenser, they release this heat to the atmosphere. So that is the function of refrigerant. So it is very important to study what are the refrigerants are used and for which application which refrigerant is used in our this refrigeration and air conditioning industry. Okay. So quickly I will take the revision of last lectures and then we can presume from the point where we stopped in last lecture. Okay, so this was a syllabus. I gave some slide about idea about this Danfoss. So Danfoss is a MNC in this field. So they are offering this online trading. Not only Danfoss, there is ASHRAE, which is also offering online trading. So we are going to study these two standards in this chapter. That is ASHRAE standard 15, which is related to safety in handling the refrigerants, and standard 34, which is related to classification and nomenclature of refrigerants. Okay. So you can go online. You can see ASHRAE is like providing online training also. So they have one module which is dedicated to refrigerants literacy. Okay, so then we saw like what are the market leaders in this field. Honeywell International is the market leader in the manufacturing of refrigerant. So this refrigerant industry is very big. Its market size is around 22 point or almost 23 billion, which was estimated in 2018. Okay, so you can imagine like this is very big industry and a lot of opportunities are there in this field. Then we started with the introduction. So refrigerant definition is given as it is the primary working fluid used for absorbing and transmitting heat in a refrigeration system. Okay. Then we started with the basic classification of refrigerants. So that was the primary refrigerants and secondary refrigerants. So what are the primary refrigerants? So if I use a VCRS system, that is vapor compression refrigeration system, for direct cooling of air, in that case we can say that whatever refrigerant is there, that is the primary refrigerant. Okay. So I have a VCRS, vapor compression refrigeration system. If I am using cooling of air, in that case whatever refrigerant we have, that we can say it is a primary refrigerant. Okay, but if I use a VCRS system first to cool another fluid, so let us say water, and that water will cool the air. So in that case whatever refrigerant used in this VCRS, that is a primary, but this water in this case, that will be called as secondary refrigerant. So primary refrigerant, they undergo the phase change process during heat absorption and heat release. But in the case of secondary refrigerant, so water, they don't undergo phase change process. They undergo only sensible cooling or sensible heating. So commonly used secondary refrigerants, those are like salt base. So in salt base, we are using water plus salt. Okay. So second, we have glycol based, in which we are using water with this ethylene glycol, propylene glycol, or calcium chloride. So this way, secondary refrigerants are used. So these are generally called as brines. So industry term for secondary refrigerant, they are called as brines. Okay. So this was our first lecture, and last I'll go quickly to the last lecture. So this was our last lecture. Okay, so after introduction, it is very important to know some important definitions related to environment. So before we go into actual classification and nomenclature of refrigerant, it is very important to study what are its effects on the environment. So first we started with some properties of thermodynamic, thermophysical properties. Then we saw environmental and safety properties, and third it was economics. So quickly I will take the revision of thermophysical properties. So first was suction pressure. So suction pressure should be as low as possible, so as high as possible. Okay, so it should not be lower than the atmospheric pressure. In case of discharge pressure, it should be as small as possible. Okay, so it allows the lightweight construction of compressor, condenser pipes, etc. Okay. The next we saw the pressure ratio. So pressure ratio should be small for like again to smaller capacity of compressors, and it will increase the volumetric efficiency and it will lower the power consumption. Then we saw the latent heat of vaporization. So latent heat of vaporization is the leading criteria in selection of refrigerants, because higher the latent heat, more heat it will absorb during the phase change. So it should be as large as possible, but we saw one relation here. So this is a relation between pressure ratio and latent heat. So they are directly proportional. So if I'm going for higher latent heat, automatically it will have higher pressure ratios. So a trade-off is needed. So we have to select the optimum values of this pressure ratio and latent heat of vaporization. Then fifth of isentropy index of compression. This should be again low, as small as possible. Liquid specific heat should be lower. Okay, but vapor specific heat should be higher. It should be as large as possible. Thermal conductivity, again, it should be larger because we want more heat transfer. So we have studied this law in HMT in first chapter, that rate of heat transfer directly proportional to rate of change of temperature, and that we used a constant as thermal conductivity K. Okay. Viscosity, again, viscosity is the resistance to the flow. So it should be as low as possible, because higher velocity, higher will be resistant to the flow, greater will be the pressure drop. Okay. So that was about thermophysical properties. Then we saw that environmental and safety properties. So in environmental, there are not four, there are three important criteria. First is ozone depletion potential. Second was global warming potential, and third it was total equivalent index sum. Okay, so that we have seen last lecture. So first we saw that ozone depletion potential. So as the name suggests, it is a potential of a gas to cause harm to the ozone layer, which is present in the stratosphere. So we all know that ozone layer is very important. It restricts the passage of UV lights, which are very harmful, not only human beings, they're also harmful for the agriculture crops. So ozone layer is very important. But what happens when we use these refrigerants, which are chlorine based? So when this chlorine or the CFC gases, chlorofluorocarbon gases go in the atmosphere, in that case what happens, this UV rays comes in contact with CFCs, then that chlorine is separated from the CFCs. That chlorine reacts with ozone, and that ozone is destructed. So it is said that if I take one molecule of chlorine, it can destruct about 1000 molecules of ozone. So the scientists have taken CFCs as a base gas here to compare this ozone depletion potential of other gases. Then based on the ozone depletion potential of CFC, other gases are numbered. Okay, so according to the Montreal Protocol, that ODP of the refrigerant should be 0. Okay, so there was a summit was conducted in 1989, 87. So it was decided that all the gases which are harmful to the ozone layer, they should be phased out. So that summit is called as the name was given to that summit. It was a Montreal Protocol. So you can search online for this Montreal Protocol. You will get good information. Another summit was conducted. So that protocol we call it as a Kyoto Protocol. So Kyoto is related to the emission of CO2 gases. That also is very important. So Montreal and Kyoto Protocol, these are very important in this environmental point of view. Okay, so next we saw that global warming potential. Again, as the name suggests, it is it measures the potential of gases or the liquids which causes the global warming. So we are very familiar with these greenhouse gases. So major greenhouses are carbon dioxide, nitrous oxides, and fluorinated gases. Okay, so all this comes under greenhouse gases. And I have told in this figure that electricity sector or power sector is the major source of production of these greenhouse gases, and the list is followed by agriculture. But how to measure this global warming potential? How we can say that this gas is very harmful, this gas is very least harmful? So we are using CO2 as a base gas. So we measure how much heat is being absorbed by CO2, and for the same mass, how much heat is absorbed by another gas. So based on CO2's heat absorption capacity, we can decide whether other gas is more harmful or less harmful. Okay, so refrigerant should have a low GWP as possible to minimize global warming. Then the next we saw that total equivalent warming index, that is TEWI. Okay, so so TEWI is very important for refrigerants. Why it is important? Because it not only it accounts the direct uh, damage caused by the refrigerant. So direct damage means when there is a leakage of refrigerant from refrigerant industry or the uh, air conditioning system. So it can directly cause global warming because it is directly emitted into the atmosphere. So that is the direct damages. But if I count indirect damages, indirect means what? Means what? So if I'm running a air conditioning plant, so it will require some electricity for running the compressor. Now that electricity will come from where? It will come from thermal power plant. Mostly it comes from thermal power plant, and that thermal power plant again it uses coal. So in that case, so while burning the coal, CO2 is released. So that will be accounted as indirect damages. Okay, so we have considered direct global warming potential and indirect global warming potential. Okay, it considers both direct due to release into atmosphere and indirect through energy consumption. Then we saw one table. So here, as I told you, for global warming potential, we are taking CO2 as a reference gas. So its GWP is 1. And other gases, they are compared with CO2. So CH4. So what this 23 indicates? That 23 times this methane is harmful than CO2. Okay. Then if I take nitrogen oxide, nitrous oxide, so that will be 296. This means that nitrous oxide can cause damage 296 times compared to CO2. Okay, so it is the highest we can see for SF6. So all these gases which are causing the global warming. So in that Kyoto Protocol, they are said to be phased out. Okay, so we saw that formula for TEWI. Okay, so in that case, we are accounting the direct losses due to leakages and indirect losses due to energy consumption. I think we stop there this point in the last lecture. We'll continue from here onwards. Okay. Okay. So we'll continue today's lecture with the remaining environmental and safety properties. Today we are dealing with safety properties. So safety properties, there are two safety properties. First is toxicity and second is flammability. Okay. So I'll read this. So toxicity is a relative term which becomes meaningful only when the degree of concentration and the time of exposure required to produce harmful effects are specified. So how you can say that a specific gas is a toxic gas? आपण म्हणतो की एखादा गॅस फार टॉक्सिक आहे आणि फार विषारी आहे असं आपण म्हणतो. But that is actually a relative term. Okay. So in that case, we have to account the degree of concentration of that gas as well as time of exposure. Okay, so it may happen that gas is having very less concentration, right, and it is exposed for very less time. That case we can say that it is having very less toxicity. But if a gas is having higher concentration and it is exposed for a longer time, in that case we have to say that that gas is very toxic. Okay, second is flammability. So it is a like ability to catch flame. So that ability we are terming it as a flammability. So the refrigerants should preferably be non-flammable and non-explosive. For flammable refrigerants, special precautions should be taken to avoid accidents. So we have this ASHRAE standard of 15, which deals with this toxicity and flammability of the refrigerants. So obviously the refrigerant should not catch fire. Okay, so that will be like destruction of this VCRA system and also destruction of the properties. So a care should be taken that a refrigerant should not be very toxic and it should not be flammable or explosive. Okay, so ASHRAE standard 15 that specifies these refrigerants, differentiates these refrigerants based on their toxicity and flammability. So that we'll see now. So based on above criteria, ASHRAE has divided refrigerants into 6 safety groups, A1 to A3 and B1 to B3. Refrigerants belonging to group A1, that is R11, R12, R22, R134A, R744, R718, are least hazardous, while refrigerants belonging to group B3, that is R1140, are most hazardous. So what this means, so that is this whatever they have said here, that been showed on this diagram. So what they are saying, if I take group A1, so it starts with A1. A1 means lower toxicity and no flame propagation. That means it is having least toxicity and least flammability. Then in that column, if I go up A2 and A2L, in that case, they are having lower toxicity but lower flammability. So slightly higher flammability compared to A1. If I go to A3, A3 will be have lower toxicity, but it will have higher flammability. It can be explosive also. If I move in the row, so next is higher toxicity. So B1 is the group which is having higher toxicity but no flame propagation. If I move in the same column, we have B2L and B2. So they are having lower flammability but higher toxicity. If I go to B3, B3 is having higher toxicity as well as higher flammability. That means B3 is B3 should be avoided. So we should not select B3 because B3 having highest toxicity and highest flammability, and we should always go for A1. A1 means lower toxicity and lower or sorry, no flame propagation. Okay, so please draw that table, so that will give you or clear your idea about toxicity and flammability. How about this table? You can write this standard also. So this is a ASHRAE standard 15. So draw that table and give the title as ASHRAE standard 15. So it specifies gas flammability and toxicity. Okay, so I hope you have completed that table. Okay, so that is the Astray standard 15. So that is why I promote Astray. They are giving very good resources and standards related to refrigeration and air conditioning, and it is always good that we are linked with such a international organization. So apart from Astray, there is the ACME is also there, and ASM is also there, American Society for Mechanical Engineers. So if you are interested in automobiles, so we have this SAE, Society of Automotive Engineers. If you are interested in plumbing, plumbing is also having one society that is called as American Society for Plumbing Engineers. So you can take any subscription, but it is always advisable that you should be a member of any international organization. Okay, so I'll show you the table related to first thermophysical properties, and then we see a table related to ODP, GWP, and toxicity. So first, this table will give some thermophysical properties of a refrigerant. So if I take R11, okay, here its boiling point is 23.80. Okay, so it is not very common to us. We have water which boils at 100 degrees Celsius, but refrigerants like R11, so it boils at temperature of plus 23.8 degrees Celsius. Then its critical pressure, if I take, so that is a 43.9. Its critical temperature is 198 degrees Celsius. Okay, for water, I think that critical temperature is 744. But in case of the refrigerant, the critical temperature it is 198. Okay, so then we have this COP. If I use R11 and if I calculate the COP, so in this case, how they are calculating COP? So they are assuming evaporator temperature at minus 50 degrees Celsius and condenser temperature at 30 degrees Celsius. If I use the R11, in that case, COP will be 5.09. Okay. Then yes, so coming here safety, so this R11 is marked as A1. So just we have seen A1 means lowest toxicity and non-flammability. So it is very safe to use. Then there is a miscibility with mineral oil, that is a good. So that refrigerant should be miscible or soluble in the oil. Oil means that whatever oil is used in the compressor. Then we have this bhp per tons. So this is brake per horsepower per ton of refrigeration. If I use R11, it is having 0.939. Okay, so the thing is R11, it is that R11 is having higher ODP, that is ozone depletion potential, and GWP, that is global warming potential, but it is not flammable and it is non-toxic. Okay, so its toxicity is very less and flammability is as equal as none. Okay, so if I take R12, so if I come here R12, you can see the boiling point is in minus degrees. Okay, so this is again uncommon to us. So it boils at temperature of minus 29.8, or you can say minus 30 degrees Celsius. So that is this boiling point. Boiling point means it is converted from liquid to vapor. Then if I come here BHP per ton, that is 0.992. COP is slightly less, 4.89. But again, the toxicity or the flammability, that is given as A1. A1 means less toxic and non-flammable. Now if I come here for R717, in that case we can see that boiling point is minus 33.3 degrees Celsius. But if I come here at this point, so it is labeled as B2 type refrigerant. B2 means it is having higher toxicity but lower flammability. So it is a highly toxic, but there is flammability, but that flammability level is very low. Okay. So this table gives you slight idea about thermophysical properties, what we are dealing in case of refrigerants. Okay. So next table, this will give you some idea about ODP and GWP. So if I take methane, okay, methane, we all know that is the CH4. If I take methane, so these are called as hydrocarbon refrigerants. So their molecular weight, we know that is a 16. Its critical temperature is given as 82.5. Then this critical pressure is given as 45.9 bar. The density is given. This this temperature is given. Okay, so that temperature is TNBP, so that is near boiling point. So its boiling point you can see here, that is a minus 161.4. Okay, so you can imagine that if I want to convert methane gas into liquid, then I have to go up to minus 161.4. So at suppose at minus 165, I can assure you that methane is converted into liquid. Then coming at ODP, so ODP, we know that ODP means ozone depletion potential. So that is a zero. That is a very good thing. The GWP for that case methane over the span of 100 years, it is given as 25. So that means that it can cause global warming 25 times that of CO2. Then life in years, so if I use methane in my VCRS system, so I should use it for 12 years. Then ASHRAE 34 safety class, so that is given by A3, so that is the standard 34, sorry that I mentioned as 15, so that is a 34. So that is mentioned as A3. A3 means it is a non-flammable, but sorry, A3 means that is having low toxicity, but it is highly flammable. It can also explode. Corrosiveness, is it a corrosive? So it is no, it is not corrosive. If I take air, so if I take air, so here is the air. Air, if I take, in that case, life is infinite. So you can use air as many times as I want in a given VCRS system, air refrigeration system. In that case also you can see it is labeled as A1. A1 means less toxic and non-flammable. Or is it a corrosive? So we know that air is not corrosive. Okay. So this way, this table gives you idea about the refrigerant, their thermophysical properties, as well as ODP, GWP, its life, and toxicity and flammability label. So here, this refrigerant they have classified as first is natural, second is blends of, and third is synthetic. So what are these types? We'll see in today's lecture how these refrigerants are being classified. That we'll see today. Okay. So any doubt up to this, you can ask. One more thing here, so methane, we know that CH4, but it is labeled as R50. If I take air, air is labeled as R729. So this we'll see today why they are labeled like this. Okay. Right. So I think no questions I see in the chat box. I will move further. Okay. So apart from this GWP, ODP, and TWI, we'll see other important properties. So first is chemical stability. Chemical stability means when I am using a refrigerant inside my VCRS system, so it should retain its chemical composition throughout its life. So if I'm using R11 for like suppose 12 years, so within that span of 11 years, so that R12 should remain as it is. Okay, so it should not undergo any chemical decomposition. So refrigerant should be chemically stable as long as they are inside the refrigeration system. Second is compatibility with common materials of construction, both metals and non-metals. That means that if I'm using a refrigerant, it should not react with the pipes in which it is flowing. Okay. So there is a case of ammonia. If I'm using ammonia for refrigeration, ammonia reacts with copper tubes. So if I'm using copper tubes, I cannot use ammonia. Or if I want to use ammonia, I cannot use copper tubes. So that care has to be taken. That refrigerant should not react with the whatever metals or non-metals inside your system. Third is miscibility with lubricating oil. So refrigerant, oil separators have to be used if the refrigerant is not miscible with lubricating oil. For example, ammonia. Refrigerants that are completely miscible with oils are easier to handle. Okay, so oil means the oil in compressor. So refrigerant, if any case, so if in any case refrigerant comes in contact with lubricating oil of compressor, So it should not, that create any another reaction and form the product. So they should be easily miscible in that oil. Fourth is dielectric strain. So this is very interesting concept. It is related to insulators, dielectric strain. So if I'm using an insulator, okay, so this principle you have not studied in HMT. You might have studied that critical thickness, but dielectric strength is something different. So I have one insulator here. So this is a suppose insulator with some thickness. Okay, and if I apply some voltage to it, okay. So dielectric strength means that voltage at up to which this insulator can retain its insulating properties. Okay, so after some voltage, suppose V1 is the voltage. After V1, if I increase the voltage in the system, that insulator will no longer act as a insulator. It will lose its insulating properties. So that strength, the maximum voltage up to which insulator can hold its insulating properties, that we call it as a dielectric strain. So it is advisable that refrigerants should also have a high dielectric strain. काय होतं जर तुम्ही व्होल्टेज डायलेक्ट्रिक स्ट्रेन पेक्षा जास्त दिलं तर त्या केसमध्ये काय होतं इट स्टार्ट्स कंडक्टिंग द इलेक्ट्रिसिटी. So it is not advisable that a refrigerant should conduct electricity inside a VCRS system. So that is why that refrigerant should have a higher dielectric strain. Okay, so this is an important property for system using hermetic compressor. For this system, the refrigerant should have as high a dielectric strain as possible. Okay. So this is very important property, dielectric strain. It is used while defining the insulators. If I am using insulator, I should know its dielectric strain, the maximum voltage it can hold, or up to which it can retain its insulating properties. Okay. So you can note down these properties. You can just give the title: chemical stability, compatibility with common materials of construction, miscibility with lubricating oils, and dielectric strain. Okay, so I hope you have taken the notes of these important properties. So that was all about environmental and safety properties. Next, we'll see the economic properties. So obviously, the refrigerant used should be preferably inexpensive and easily available. Okay, so quickly I will show you the prices of refrigerant. Okay, so if I go on net, and if I search for a refrigerant, if I go for like let us say I go for India Mart, so refrigerant pricing. So India Mart, you can check like what are the prices of refrigeration gas it is being used. So there are they are available in the cylinders. So per cylinder you have to take it. Okay. So here you can say if I'm buying R134A, in that case that price is 390 per can. Okay. If I'm using R134A, here its price is high. It is like 405 per kilogram. Okay. And the whole that can weight it is 102 kg. So multiply by 405, that will be the weight of that total can. So it depends on weight. Okay. So they have given in the form of table also here. It is said that if I buy 134A, it is like 390 per kg. Okay. R22 it is 380 per kg. 404 it is 400 per kg. R410A it is priced at 350 per kg. So you can say that refrigerants are priced on an average 400 per kg. Okay, so that cylinder, if it contains 15 liter cylinder, it is there. So 15 into 400, that will be the price of that refrigerant cylinder. Okay, so that was about the pricing and economic considerations. Okay, so up to now we have covered only properties, thermophysical, environmental, and safety properties, and lastly economic properties. Okay, so this whatever price of refrigerant used that will be accounted in your bill of materials. So if I am a refrigeration engineer and I am going to design one refrigeration system, suppose a milk cooling plant if it is there. So in that system on my bill of material everything will be there. So there will be evaporator, condenser, then copper tubing, then insulation, then the refrigerant amount of refrigerant used. So that will be counted in that. And finally, I will prepare one business plan in which there will be cost of the plant, only that refrigeration system. Then there will be like initial cost, then operating cost, then there will be wages of workers. So all that will be included in my business plan. Okay. So that is all about properties. Today we'll see how these refrigerants are classified and how this nomenclature works. Okay. Okay, so nomenclature of refrigerants. First, we'll see the differentiation or the classification. Then we can move towards the nomenclature. Okay, so I'll read this. Since a large number of refrigerants have been developed over the years for a wide variety of applications, a numbering system has been adopted to designate various refrigerants. From the number 1, we can get some useful information about the type of refrigerant, its chemical composition, molecular weight, etc. All the refrigerants are designated by R followed by a unique number. So whenever you say R11, R12, R404, remember that R stands for refrigerant. Okay. So if I say write down the uh, like nomenclature for chlorofluorocarbon, in that case, first letter you should write that is a R. Then that whatever number comes, that will be there. So it is a R12 or 11. That way we are writing the names of refrigerants. Okay. So first we'll see the classification. These refrigerants are majorly classified into first pure fluids and that is second is mixtures. Again, these pure fluids are classified into synthetics. Okay, these are also called as halocarbons. Okay, and second is natural. Under natural we have organic, that is hydrocarbons, and second is inorganic. So HC means hydrocarbons. Okay, so we have been hearing these terms organic and inorganic since our 11th and 12th standard. In that we have studied organic chemistry and inorganic chemistry. So can anybody give me idea what is the difference between organic and inorganic? So why they are classified as organic and inorganic? Why we are studying organic chemistry separately and inorganic chemistry separately? Does anybody knows? So I have one answer. Organic contains carbon and inorganic means without carbon. But as you can see on the screen, under inorganic I have written CO2. CO2 contains carbon. So whatever you say, that fits there. So what should be the reason behind organic and inorganic? Why we have classified chemistry into organic chemistry and inorganic chemistry? Yes, anybody? So you must have studied in your 12th organic chemistry and inorganic chemistry. At that time, uh, didn't this question arise in your mind that why there are two streams separate, organic and inorganic? Okay, I'll tell you the difference, but remember always, whenever you are curious about something, don't kill your curiosity. Always take further your curiosity. So whenever you are studying in 12th, that question should have arise in your mind. Why we are studying two different streams, that organic chemistry and inorganic chemistry. So I'll tell you the difference. So see, the thing here it is, organic means we have carbon and hydrogen bonds. So Rohit, your answer is partially correct. The thing is, organic chemistry deals with carbon and hydrogen bonds. Inorganic chemistry does not deal with carbon and hydrogen bonds. Again, organic, whatever chemicals we are getting, that are product of activities carried out by humans and animals. Okay, so that are the products of living organisms. But inorganics not necessarily has to be product of living organisms. Okay, so they are readily available in the nature. If I take example of air, water, they are available in the nature from the ages. So that comes under inorganic chemicals. But if I take whatever gases trapped under the earth crust, so like methane, ethane, methanol, ethanol, so that will be considered under organic chemicals. Okay, so that is a major difference. Carbon and hydrogen atoms bonds are studied under organic, and those are not studied in inorganic. Right? So write down this classification. Refrigerants. The first classification we have pure fluids, and second is mixture. So we have studied up to pure fluids. So what are the mixture that we will also study? So mixtures here, first mixture we have azeotropic and second is zeotropic. What are those? We'll see in the next slides. But remember, this refrigerants first classified as pure fluids. So pure fluids mean they are having only one chemical composition. In mixtures, we are mixing two or more refrigerants together, and we are getting some mixture. Okay. Under pure fluids, they are classified as synthetic. Synthetics are also called as halocarbons. And the second classification is natural. Under natural, we have organic and inorganic. Organic are also called as hydrocarbons. Hydrocarbons you might have studied. Those are like methane, ethane, and methanol, ethanol. So those are like hydrocarbons. So draw this diagram or write down this classification of refrigerants. Okay, so we have Ganesh Kumar. He's saying A32. Ganesh Kumar, please attend lectures on time. And there is a time when I take attendance. Then no need to give your roll number. Okay. So if I observe that you leave this lecture after giving your roll number, anyway, I'm not going to count your attendance. Okay. Okay. So I hope you have noted down this classification. Now we'll see one by one. Okay, so we have ASTRE standard 34, which deals with this classification. So number assigned to each refrigerant is related to its chemical composition, and the system is formalized as ASTRE standard 34. Broadly, the numbering system is as follows. So 0 series is methane based, 100 series is ethane based, 200 series is propane based, 300 series is cyclic organic compounds, 400 is zeotrops, so that is a mixture. 500 series is azeotrophs, so again that is a mixture. 600 series is the organic compounds, so those are like hydrocarbons. 700 series is organic inorganic compounds, so those are water, air, carbon dioxide, nitrogen dioxide. 1000 series is for unsaturated organic compounds. Unsaturated means if I take methane, so that formula is CH4. If I take CH3, so that will be in unsaturated organic compound. So we have ethane C2H6, but if I take C2H4, we know that it needs two more hydrogen atoms. So in that case, that becomes unsaturated organic compounds. Okay, so again I will explain this what is meant by unsaturated organic compound. So saturated means that is CH4. CH4 means, or if I take C2H6, so we know that this is written in this format C2C. Hydrogen, 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 and hydrogen. So this is a chemical diagram or this C2H6, that is a ethane. Okay, but if I cancel these two hydrogen atoms, so that will become C2H4. Okay, so C2H4, C2H4. So in that case, it needs two more hydrogen atoms. In that case, that becomes unsaturated organic compound. It needs two more hydrogen atoms. Okay, that way it will be chemically stable. Right. Okay. So first we'll start with the halogenated compounds. So that is a synthetic refrigerants. So these refrigerants are derivatives of alkanes such as methane, ethane, and propane. These refrigerants are designated by RXYZ. Okay, so this is a general uh, formula which is given for this fully saturated halogenated compounds. Halogenated means that are the synthetic refrigerants. Okay, synthetic refrigerants. So those are the derivatives of the methane, ethane, or propane. In general, we call them as alkanes. So you know that formula for alkanes, it is CnH2n plus 2n. Means if I take n as 1, so here H will be 2 plus 2, 4. So that will be CH4, that means methane. Okay, so these refrigerants are designated by RXYZ. So this is the general formula in which X plus 1 indicates the number of carbon atoms. Okay, so if they have given X as 1, 1 plus 1, that means 2 will be carbon atoms. Y minus 1 indicates the number of hydrogen atoms. Suppose Y is again 2, so 2 minus 1, that is 1 will be hydrogen atoms. Z indicates number of fluorine atoms. So suppose Z is 2, in that case 2 will be number of fluorine atoms. And the remaining chlorine, so chlorine, how to find out chlorine? The balance indicates the number of chlorine atoms. Balance means number of atoms that can be attached to carbon. Okay, number of atoms that can be attached to carbon means If I take CH4, in that case, number of atoms that can be attached to carbon that are 4. If I take example of C2H6, that is ethane, in that case, number of atoms that can be attached to carbon that are 6. Okay, minus number of hydrogen plus fluorine atoms. Okay, so this is the formula to calculate the number of chlorine atoms. Now, if only 2 digits indicates that the value of X is 0. So, if I take R11, so in that case, there are only 2 digits, that means X is 0. So, I'll take quickly one example. If I take example of R12, okay, I will compare this RXYZ, XYZ. So, if this is having only 2 digits, that means X will be 0. Okay, so number of carbon atoms will be equal to X plus 1, so that will be 1. 1 means this is a ethane base, sorry, this is a methane base. This is a methane based product. Why? Because carbon atoms are 1. So we know that methane is CH4, only one carbon atom is there. So that is why this refrigerant is methane based. Then next, Y, here in the case Y is equal to 1. So Y is equal to 1. So we can say that number of hydrogen atoms will be equal to Y minus 1, that will be 0. Again, Z indicates number of fluorine atoms. So Z here it is 2. So number of fluorine atoms will be equal to 2. How to calculate number of fluorine atoms? So I will continue here. Number of chlorine atoms this will be equal to, so as this is a methane base, so in methane how many atoms that we can attach to carbon? That is 4, minus number of hydrogen and fluorine atoms. So number of hydrogen atoms here it is 0, plus number of fluorine atoms, that is 2. So this will be 2. So number of chlorine atoms that are 2. So I can write the formula here it is as a number of carbon atoms, that is C1, that is C. Number of hydrogen atoms, that is 0. So no need to write H. Then we have number of chlorine atoms, that is 2. So that will be CCl2. Number of fluorine atoms we have F2. So this is a difluoromethane. Okay, so that's how we name this as a dimethylfluoromethane. Why it is methane? Because it is only one carbon. Okay, so I will repeat this process again. I am having one refrigerant which is R12. Okay, so we know the general formula here it is RXYZ, in which X indicates number of carbon atoms, sorry, X plus 1 indicates number of carbon atoms, Y minus 1 indicates hydrogen atoms, and Z indicates number of fluorine atoms. If there are only two numbers here, that means X is equal to 0. Okay, so there are only two numbers, that means X is equal to 0. So number of carbon atoms equal to X plus 1 equal to 1, 0 plus 1 equal to 1. In this case, Y is equal to 1. So after X, that is Y, that is 1. So this is Y and Z. X is 0. Y is given as 1. So number of hydrogen atoms, that will equal to Y minus 1 equal to 1 minus 1 equal to 0. Okay. Then Z is equal to 2. So number of chlorine atoms equal to Z, that is equal to 2. Now remaining part is number of chlorine atoms. Number of chlorine atoms will be equal to number of atoms that can be attached to the carbon. So in this case, there is only one carbon, that means it is a methane base. So in methane, we can attach four hydrogens to one carbon, so that number will be 4. So 4 minus number of hydrogen and fluorine atoms. So 0 plus 2, that will be 2. So we have one carbon atom, we have two fluorine atoms, we have two chlorine atoms. So that formula will be CCl2F2. This can be written as difluoromethane. Okay. So this way it was. I'll give you some practice, so you can practice it. So I'll give one example, then you have to tell me the name. So that will be R22. So you have to calculate number of hydrogen, number of carbon, number of fluorine, and number of chlorine atoms. After that, you can write the name. So I have one question here. To name it is a methane, hydrogen should be there. Without hydrogen, it will be carbon only. So yes, so I have used the term as methane base. I didn't use it is a methane. So it is a methane base. That is why we are using methane. So that name is difluoromethane. Okay. So I have given one example R22. From this, you have to calculate number of uh, hydrogen, carbon, fluorine, and chlorine atoms. After that, you can write the formula also and name also. Okay. So for reference, so I will keep this tab open, and from this you have to calculate the formula for R22. So others, please make some efforts. I have explained you how to derive a name for R12. Similar approach you can use for R22. You have to derive a formula and mention its name for R22. Okay, so I have two answers here. CHClF2. Description Saurabh Bhosle. He has given description as chloro difluoromethane. Okay, so I will try to solve this. Others, please follow. Okay, so we are dealing with R22. We know we have the formula as RXYZ. There are only two digits. That means X will be equal to 0. So number of carbon atoms are equal to X plus 1. So that will be 0 plus 1, 1. So that means this is a methane base. We have only one carbon. That means it is a methane base. Second, we have Y is equal to 2. So number of hydrogen atoms equal to Y minus 1. So in this case, 2 minus 1, that is the 1. So we have hydrogen atoms as 1. Next is number of fluorine atoms. So those are equal to Z. Z is in this case it is equal to 2. Now number of chlorine atoms, this is equal to, so this is equal to number of atoms that can be attached to to the given carbon. So it is a methane base. So for methane, CH4, we can say that for a one carbon atom, four hydrogen atoms are attached. So that four number here you have to write minus number of hydrogen and fluorine atoms. So hydrogen atom it is 1 plus fluorine atoms that are 2. So is equal to 1. Okay. So this way I have derived this values for carbon, hydrogen, fluorine and chlorine. Okay. So how many of you got this answer? Okay, so we can write this chemical formula now. So first will be carbon, followed by hydrogen, one hydrogen, then followed by chlorine. So that will be Cl. I think one Cl is there, and though there are two fluorine atoms, so this will be its formula: one carbon atom, one hydrogen atom, followed by chlorine and fluorine. So remember this sequence also. First comes carbon, then comes hydrogen, then comes chlorine, then comes fluorine. If I want to write its name will be chloro. I can simply write chloro. Instead of that, I will write monochloro. Okay, monochloro. Then there will be difluoro. Then there will be, is it a methane or ethane? So this is a methane. So this will be methane. So we have monochloro, difluoro, methane. So that is nothing but R22. Okay. So I hope you understood this simple mathematical calculation. It is there. I will give one more refrigerant. So that is R134. And you have to similarly derive its name and chemical formula. So this time I expect more participation. So you have to derive a chemical composition and name for R134. Okay, so I have some answers. I will try to solve it. Okay, so we are dealing with now with R134. So I'll compare this with standard its structure. So that is Rxyz. So in this case, I can directly say X is equal to 1. So number of carbon atoms, this case is equal to X plus 1. So that is equal to 1 plus 1, that would be 2. That means this is a ethane based product. Ethane based. We have 2 carbons. Okay. Then next is number of fluorine atoms, sorry, hydrogen atoms. So we know that it is equal to y minus 1. So y, you can say here y is equal to 3 and we have z is equal to 4. So this will be equal to 3 minus 1, that would be 2. Then we have number of, just write down it, number of fluorine atoms equal to z, z equal to 4 is given in this case. Last is number of chlorine atoms. So number of, see here, our product is ethane base. Ethane's formula is C2H6. So we can say that for carbon atoms, number of hydrogen atoms that can be attached, it is a 6. So we have to take here 6. 6 minus number of hydrogen plus fluorine atoms. Number of hydrogen atoms here it is 2 plus number of fluorine atoms, that is 4. 6 minus 6, that will be 0. So number of fluorine atoms, that will be 0. So we have 2 carbon atoms, then we have 2 hydrogen atoms and 4 fluorine atoms. Okay, so this formula many of you have written in the answer. I will write that as it is. So Sirsa's hydrogen, this has a C2H2F4. But if you see its chemical composition, it is more like a CF3. Then we have CF, we have CHF. So something like this, we have this composition. So this is called as tetra. So as Rohit has rightly mentioned, it is a tetrafluorine ethane. Okay, so it is a tetrafluoro. So we have 4 fluorine atoms. That is why it is a tetra. If it was a 3, it will be tri. But we have 4 fluorine atoms, so that will be tetrafluoro. And this is a ethane. So that will be tetrafluoroethane. Okay, so this answer, if you have got, it is like mathematically it may be correct, but if you go for chemical composition, this will be its structure. This I will show you how it looks. So CF3CHL, so this will be like C. It is attached to 3 fluorine atoms. So we know that fluorine and chlorine, they have deficiency of 1 atom. So it is attached to another carbon atom. Then we have 2 fluorine atoms and 1 hydrogen atom. So this will be CF3CHFL2. Okay. Sorry. This is FL. This is the FL. Sorry, this is the F. CF3CHF. Okay. So this will be the name or the formula for the R134. So again we have R134A. So I think Rohit has searched on Google. So I'll explain that also. So we were up to this point. So only 2 digits. That means X is equal to 0. Next point, I will read. So letter A stands for isomer. That is molecules having same chemical composition but different atomic arrangement. So we have R134 and R134A. So they are having same number of carbon, hydrogen and fluorine atoms, but their structure will be different. So that is called as isomer. So they are having same composition but different atomic arrangement. So that is called as isomer. Okay. So you can practice this for other atoms, for other refrigerant also. So we have R11, we have R12, we have. So you can practice for this. You can obtain the name. Okay. Okay, so for R134, I have corrected the answer. That will be CF3, CH2F. Okay, so number of fluorine atoms will be 4. Number of hydrogen atoms will be 2. Okay, number of carbon atoms will be 2. So that is the R22. First we have discussed, and then we have derived for R134. Similar approach you can go for R11 and R22. This formula and this nomenclature, it is valid for only synthetic refrigerant, or general we call them as a halocarbons. Okay, what we call them as a halocarbons. So you cannot use this for organic and inorganic components. Okay, so that is all about synthetic refrigerants. So we have seen their nomenclature and their classification. Next, we'll see inorganic refrigerants. So we have organic refrigerants, which are called as hydrocarbons. And the second, we have inorganic refrigerants. So they both come under natural refrigerants. Okay, so we are not talking about natural refrigerants. Under natural refrigerants, we have organic, which are called as hydrocarbons. Under that, we have inorganic. The common examples of inorganic are air and water. Okay, so these are designated by number 7, followed by the molecular weight of the refrigerant. Okay, so we all know that if I want to specify refrigerant, first letter that should be R, and if R is followed by 7, that means we are talking about inorganic refrigerants. Okay, now whatever followed by R7, that will be the molecular weight of that chemical. So first example I will take here, that is ammonia. Ammonia, we know that ammonia, that is nothing but NH3. So molecular or atomic weight of nitrogen, that is 14. Atomic weight of hydrogen, that is 1. 1 into 3, that will be 3. So total molecular weight of NH3, that is 17. So designation will be R717. Here it will be R717. Okay. So whenever you find out R7 and some number is there, so R7 means that is the inorganic refrigerant. Okay, R7 also stands for Ronaldo 7 number jersey, but okay, that is different part. R717, that is for inorganic refrigerants. Okay, so if I take example of carbon dioxide, in that case, again, I have to first write down it as R7, then I have to calculate molecular weight of carbon dioxide, that is 44. So that will be R744. If I take water as a refrigerant, in that case, R7 will be there, followed by molecular weight of water. So we all know that molecular weight of water, H2O, that is the 18. So that will be R718. Okay, so this is the nomenclature for inorganic refrigerants. So write down. Okay, so I hope you have taken the notes for inorganic refrigerants. So moving on, we have a mixture. Okay, so we have seen the classification of refrigerants. In that case, first was major classification was pure fluids and mixtures. Okay, so we have seen pure fluids, that is the synthetic refrigerants and inorganic refrigerants. Now we'll see the mixtures. So mixtures, as the name suggests, we are mixing two or more refrigerants and we are forming another refrigerant. So that will be come under mixtures. In that we have two types, azeotropic and zeotropic. So the main difference between them is in its boiling point, NBP, what we call it as NBP means normal boiling point. So whatever refrigerants we are mixing together, if they have same boiling point, so whatever mixture is formed, that mixture we are calling it as a azeotropic mixture. If the refrigerants we are mixing together, if they are having different normal boiling points, in that case, whatever mixture is formed, that we are calling it as a zeotropic mixture. So that is the main difference. They are differentiated by the boiling points of the refrigerants which are being mixed together. Okay, so I'll read it. Components of isotropic mixtures boil at the same temperature, while the components of geotropic mixtures have different boiling points. Now, important point here it is, azeotropic mixtures are designated by 500 series, whereas zeotropic refrigerants, that is non-isotropic mixtures, are designated by 400 series. Okay. So, in last previous slide, I have told you if I come across R7, that will be by default inorganic refrigerant, R followed by 7. Now, in this case, if R is followed by 5, so that will be azeotropic mixture. If R is followed by 4, that will be zeotropic mixture. We'll see some examples here. So first, azeotropic mixture. So we have first as R500. So R500 is a mixture of R12 in 73.8% and R152A in 26.2%. R152A, that is nothing but difluoroethane. Okay. So it has similar characteristics as R134A, which we have seen. Okay, so if I mix together these two, R12 and R152A, I'll get a R500 azeotropic mixture. So that concentration also should be the same. Then next is R502. This is a mixture of R22 and R115. We have R503, that is a mixture of R23 and R13. We have R507A. So A stands for isobars. So there is a mixture of R125 and R143A. Okay. Coming to the zeotropic mixture, so these are for R followed by 4. So this is R followed by 5. This is R followed by 4. So first is R404A. This is a mixture of R125, R143A, and R134A. So that proportion is also has to be exact. Similarly, if I do for others, so if I go for R407A, this is a mixture of R32. So now R32 is very now famous in market because of its zero ozone depletion potential and low GWP. R32 is now being used and it has replaced our old refrigerants such as R11, R12. Then we have mixing together R125 and R134A. Okay. So this way we are getting the mixture. I'll tell you what happens when you have difference between the boiling points. So if I take a jar, so I'll draw quickly a jar. Okay. If I pour some zeotropic mixture into it, so it has some zeotropic mixture into it up to this level. Okay. So it has a zeotropic refrigerant. Now, as soon as I heat this refrigerant, if I supply some heat to this, okay, so there is a burner I have used. In this case, what happens? Whichever is having lower boiling point, so that will be evaporated first. Okay, so that will be converted into vapor. So as we know, vapor is having low density. This will be accumulated at the top. Suppose this zeotropic mixture is a mixture of several refrigerants, let us say R1 plus R2 plus R3. So that R1 is having lowest boiling point, so that will first converted into vapor, so R1, then followed by R2. So because there is a difference between the boiling points, after some temperature, R1 is converted into vapor. If I heat more, then R2 will be converted into vapor. This will be accumulated in between this. Because of density difference, we can clearly see these three mixtures are having different layers. Okay, that is about zeotropic refrigerant. They are having difference in their boiling point. If I heat them, I can easily observe these different layers are being formed on this refrigerant. Okay, this is not the case in azeotropic. Azeotropic मध्ये कसं आहे की तुम्ही हीट केलं तरी azeotropic mixture मध्ये तुम्ही हीट केलं तरी ते त्याचं काय there will be no difference in boiling point. Hence there will be no case in which we have vapor and liquid of refrigerant together. So but this can happen in case of zeotropic refrigerant. Zeotropic मध्ये एक केस अशी येऊ शकते की जसं टेम्परेचर वाढेल तसं त्यातलं एक रेफ्रिजरंट सेपरेट होऊन त्याचं वेपर होईल आणि बाकीचे लिक्विड मध्ये असतील. बट इन केस ऑफ azeotropic this cannot happen. Okay, so this is the main difference between azeotropic and zeotropic. Okay, so we just now seen the azeotropic mixtures and zeotropic mixtures. And last we'll see hydrocarbons. So hydrocarbons comes under natural refrigerants. Okay, so let me remind you this classification what we have seen in at the start. So refrigerants, first they are classified as pure fluids and mixtures. In pure fluids they are classified as synthetic, also known as halocarbons, and second was natural. In natural we have organic, that is hydrocarbons, and inorganic. Second classification was mixtures, in that we have azeotropic and zeotropic. So these are the mixtures. The last thing we are dealing here with hydrocarbons. Hydrocarbons, so as you know, that is contains carbon and hydrogen bonds. So here, for example, they have given as propane, that's the C3H8. Its refrigerant name it is R290. Then we have N-butane, that is R600. Then there is isobutane, that is the R600A. Okay. So this is also I have specified you in one PPT here. So if I using 600, that will be organic compounds. Okay. If I using 200 series, that just shown you the R290. So R290 is nothing but the propane. So that is the propane base. That is a 200 series. And if I have other organic compounds, that will be 600 series. Okay, so I have here propane 290, 200 series, then R600, R600A, that are the organic compounds. In the same hydrocarbons, I have unsaturated hydrocarbons. I have told you about the unsaturated hydrocarbons. So thing is CH4, we can say that it is saturated because it has a carbon which has attached to 4 hydrogen atoms. But if I remove any one of this, if I remove this hydrogen atom, it becomes CH3. So this is a unsaturated organic compound. Okay. So unsaturated hydrocarbons, the 1000 series has been assigned to unsaturated organic compounds. So examples are there, R1150, so that is C2H4. So saturated version will be C2H6, but I have I have deficiency of 2 hydrogen atoms, so that is the C2H4. That is why it is the unsaturated hydrocarbon. Next is R1270. Again here it is C3H6. So saturated version we know that is a C3H8. So the general formula it is CnH2n plus 2 for the alkanes. Okay. So we are at the end of this. Quickly we'll see what are the alternate refrigerants. So we have seen that ozone depletion potential and global warming potential of refrigerants. So in that one of the summits, Kyoto and Montreal summit, it was decided whatever the chemicals which are responsible for ozone layer depletion, that has to be phased out. Then after phasing out, what are their alternate refrigerants we are now using? That we'll see in next slide, and then we'll stop. Okay. So we are at the end, and I want you to write this hydrocarbons and unsaturated hydrocarbons. Then I can move to the next slide. So if you are finished with this, write down this slide also. This will summarize all the series we are studying. So 0 series it is methane based, 100 series ethane based, then all the series. So write down a short note. Okay. So I hope you have written this. This will give you handy guidance in identifying a refrigerant. Okay. So if it is a R12, that means that will be methane based. If it is R112, that will be ethane based. If it is R290, that will be propane based. If it is like the R1050, so that will be unsaturated organic compounds. So that way you can identify it. If it is a R400 something, that will be geotropes. If it is like R510, so that will be azeotrophs. Okay. So based on these numbers, you can identify to which classification that refrigerant belongs to. Okay. So now we'll see alternate refrigerants. Okay. So in the view of environmental problems caused by the synthetic refrigerants, opinions differed on the replacements of conventional refrigerants. The alternate refrigerants can be classified into two broad groups: non-ODS. ODS means non-depletion, ozone depletion potential. So non-ODS. Synthetic refrigerant based on hydrofluorocarbons. So that chlorine is totally eliminated. So we have hydrofluorocarbons and their blends. Natural refrigerants including ammonia, carbon dioxide, hydrocarbons and their blends. Okay. So we'll see what were the old refrigerants we were using, and they got phased out because of their ozone depletion potential and global warming potential. And what are the alternate refrigerants nowadays we are using? That we'll see now. So first in our list there is the R11. Okay, so R11, this refrigerant is the specific property of this. It is that it is non-toxic and non-flammable. Okay, but because of its ozone depletion potential and global warming potential, it has been phased out. So you can see here, its ozone depletion potential it is 1. Okay, because it is a CFC, and global warming potential it is a 3500. Okay, so we don't want this, so we are phasing out R11. So application previously it was used for large air conditioning system, industrial heat pumps, and as slow blowing agent. Okay. Now as this is phased out, now we are using substitute at R123, R141B, R245FA, and pentane. Okay. So these refrigerants are being used as alternate refrigerants to R11. Right. Similarly, we have R12 here. R12 you can see here is ozone depletion potential is 1, global warming potential it is 7300, and it was previously used in domestic refrigerators, small air conditioners, water coolers, small cold storages. Now as it is phased out, now it is replaced with R22. R22 will also be phased out in the coming years. Then R134A, so this is very good refrigerant. It is widely used in many of the applications. Then we have R227, R401A, R11A, R717. So this is a ammonia. Organic compound. 17 is the molecular weight of ammonia. So that will be NH3. Okay. Then we have R22, which is a HCFC. Ozone depletion potential it is 0.05. So you can see that ozone depletion potential, though it is very low as 0.05, still we don't want that also. So it is being phased out. And its global warming potential it is 1500. So previously it was used in air conditioning systems and cold storages. Now it is being replaced by R410A, R417A, R407, R507. 500 series belongs to geotrophs. Okay, R404 that belongs to azeotrophs. Again R717 that is the ammonia. Ammonia is the best refrigerant you will get in market, but its problem it is that it is very toxic. You know that जेव्हा एखादं अन्न असतं फार दिवस आपण स्टोअर करतो त्यातून आपल्याला एक गॅस बाहेर पडतो and that gas is very toxic. That gas is nothing but ammonia. So if you eat that food, chances are there that food poisoning will happen, and you may will be hospitalized. Okay, so that ammonia gas is very toxic to human beings. So where there are plants which are using ammonia as a refrigerant, there they are using this sensors are used to detect its leak. Whenever leakage happens, that sensor will give the information to the operator, and then he can detect where the leakage is taking place. But apart from that toxicity, ammonia is very good refrigerant. It is it has zero ozone depletion potential and very low global warming potential. Okay. Next, R134A HFCs, hydrofluorocarbons. So their ozone depletion potential is 0, which is very good, but their global warming potential is 1200. It is used as replacement for R12 in domestic refrigerators, water coolers, automobile ACs, etc. So for R134, no replacement is required. It is immiscible in mineral oils, and it is highly hygroscopic. So anybody knows what is the meaning of hygroscopic? Hygroscopic, anybody knows? Okay, so I'll tell hygroscopic means it is a tendency to absorb the moisture or the water. So that is a tendency, we call it as a hygroscopic. So R134 has a large tendency to absorb the moisture. Okay, but no replacement is required. Then we have R717, just now I explained about it, that is ammonia. So it is used in cold storage. So you can see here its ozone depletion potential is zero, and its global warming potential is also zero. It is used in cold storages, ice plants, food processing plants, frozen food cabinets. Here also no replacement is required. So I told you that it is highly toxic and flammable. It is also incompatible with copper. We cannot use copper tubes. But apart from that, it is highly efficient and it is inexpensive and available. Last refrigerant in our list, it is here. It is that is R744. So you can see that R7 stands for inorganic refrigerant, followed by the molecular weight. So 44 is the molecular weight of CO2. That means we are dealing with CO2. So R744, it is a CO2. You can see its ozone depletion potential is zero, okay, but it has global warming potential as 1 because we are using CO2 as a reference gas in determining global warming potential. So CO2 is used in cold storages, air conditioning system, simultaneous cooling and heating. So these transcritical cycles are there in that it is used. For this also no replacement is required. So it is having very low critical temperature which is not desirable. So as I told you, a refrigerant should have high critical pressure and low freezing point. But apart from that, it is saying eco-friendly. I don't know how they are saying it is eco-friendly because it is have a global warming potential. Maybe they are saying eco-friendly because it is having ozone depletion potential as zero. Again, it is inexpensive and available. Okay, so that is about CO2. So this is about alternate refrigerants. So there were some refrigerants which were using because of its ozone depletion potential and global warming potential. They are being phased out, and other refrigerants have taken their place. That is why they are called as alternate refrigerants. Okay. So with this, our this chapter ends. I have covered all the points of this chapter. Again, I advise you that there are other online platforms are there, which I told you about. Danfoss is providing online training. Also, Ashray is providing online training. They have their online courses related to refrigeration, air conditioning. If you are more interested, you can check that also. So whatever classification, nomenclature, properties related to refrigerant that I have covered in this chapter. And with this, our chapter ends. So soon I will release its assignment also. I will provide its additional notes, handwritten notes. The thing is that there is a lockdown in Pandharpur. I cannot go to the college and create that scanned copy. But as soon as the lockdown gets over, or in between, I can go to the college and I will create the scan notes of this our chapter, and I will provide to you. Okay. So meanwhile, I will provide you that NPTEL notes and this PPTs also. Okay. Uh, right. So in next lecture, we'll take one MCQ test like we take usually on quizzes.com in our next lecture on Monday. Okay. So wish you all a very happy Independence Day in advance. Tomorrow we are organizing one speech competition at morning, and we are organizing one essay competition throughout the day. So those who are interested, they can contact me. I will provide their names, and also I have given the numbers of teachers in one message I have posted on our group also. Okay. So quickly I will take the attendance. So bear with me.